please put a warm welcome to Dr. Lorenzo Conti.
Good morning, Chicago. At Crover, we're defining a new category of unmanned systems, that of devices able to swim below the ground through solid granular particles, like sand, grain, and powders, what we call a Crover robot. And today, we will explore the scientific discovery that made the development of the Crover robot possible, as well as some of the industrial applications that it enables, from grain storage management to space exploration. As humans, we can make rocket ships reach into space and build vessels that travel miles below the ocean. Yet, apart from our work at Crover, all attempts by other teams at developing a device that could burrow its way through sand and other granular environments have been unable to achieve full range of motion when fully submerged below the ground. What all other attempts have in common is that they used one of the methods of locomotion that you see on the left of the screen, or a combination of these. And that is really at the core of why they've not succeeded, as no device using the first three methods has been able to move without external propulsion when fully buried below the surface, and devices using the fourth method are limited to motion in a single direction. And if we look at what happens when an object is pushed through granular particles, it is easy to see why. In order for the object to move, there are a lot of particles and force chains that have to be displaced both upstream and downstream of the moving object, which requires a lot of energy and results in very large drag forces that prevent the object from moving. And so one day, during my PhD at the University of Edinburgh, I was inspired, and I started thinking, what if there was a more efficient way of moving through granular media? And so I had an intuition, the intuition that an object rotating when surrounded by granular particles would rise against gravity. And so I set up some simple experiments and simulations. And to my surprise as well, when the motor would start rotating, the device would rise to the top. This led to discovering what we call the Crover effect, which is the presence of coupling or a connection between rotational and translational motion in granular materials. What this means is that if we rotate even a symmetric object like a sphere or a cylinder while surrounded by granular particles, that rotation alone is enough to make the object move in a straight line. And it works the other way around as well. If we have an object moving linearly through granular media, that simple motion is enough to make the object rotate. Why does this matter? Unlike the other methods of locomotion that we mentioned earlier, this only requires frictional forces to be overcome instead of large drag forces, and represents the first feasible method of locomotion through granular media. Think of it as drone wings, but for the underground of granular environments. And while this may seem like a simple concept, after all, what we're saying is we rotate something and it moves. From a physics perspective, this is very counterintuitive, because we know that the same thing would not happen if the same object was rotating while surrounded by a fluid or any other static particles that are not granular. Using this technology, our team was able to develop what was and still is the first and only device in the world able to move itself in every direction in bulk, solids, and powders, what we call a Crover robot. This is opening new possibilities for researchers and bulk solids and powders professionals across Europe and the US. Some, for instance, are using the Crover robot to devise experiments which, instead of using traditional methods and assuming that conditions are uniform across the entire bulk, thanks to the Crover robot, they can capture gradients of conditions and take more advanced measurements in situ. Having solved the problem of subterranean granular locomotion, we also developed the Crover mothership, which breaks yet another big barrier, that of being able to carry heavy payloads on steep, unstable granular slopes, and doing so in a fast and stable manner. Something also which no other device, whether at a research or at an industrial level, has been able to achieve. And so after working closely with grain storage operators, listening to their needs, and after countless prototype iterations, we developed the Crover Grain Storage Management System. This includes a module for sensing grain condition, which measures parameters like temperature, moisture, and CO2, inspecting grain conditions while the robot swims through the grain, as well as a module for collecting grain samples from deep within the bulk. The movement of the Crover robot also helps steering and maintaining the quality of the grain. The data collected by the Crover robot is then sent wirelessly to our companion web app, from which grain storage operators receive a notification if grain conditions exceed a safe threshold, and they can visualize 3D and 2D maps of conditions which enable them to identify hotspots, wet spots, and plan the best course of action. The system not only samples grain bulks in line with the requirements of international standards for cereals, oilseeds, and feed, like those that form the basis of the GAFTA and REC Tractor guidelines. It also represents the new state-of-the-art for the sensing and sampling of grain bulks. For grain storage operators like farmers, grain merchants, cooperatives, and ports, this means, one, improved health and safety, by no longer requiring people to walk on grain bulks to collect samples and measurements, which is very dangerous to do and can lead to death through entrapment. Two, it overcomes the limitations of static sensors, which are usually unable to detect gradients of conditions between one sensor and the other, and often identify infestations and other issues too late. This results in an improved grain supply chain, where grain storage currently represents the single phase with the highest post-harvest losses before consumption. And so our mission at Crover is to make sure that at least 80% more grain where our system is used reaches the end of the supply chain with the same or better quality than it left the field with. This mission is being led by our team from offices in Scotland and in upstate New York. In fact, I realized quite early on that pioneering a new field like we're doing is not possible alone. It needs to be empowered together. And so starting from our core expertise in granular locomotion, we have built a team with expertise ranging from robotics and automation to grain storage and certification for dust explosive atmospheres. And we're fortunate to have a very diverse group representing 11 different nationalities. When taking a new technology to market, it is important to ensure compliance and certification. And so we set up within our headquarters at the National Robotarium in Edinburgh capabilities to test the prototypes and products that we developed against some of the most stringent international standards. And what you've seen has been the result of years of research and development. And we continue to work with grain storage operators to continue pushing the boundaries of granular locomotion and improving grain storage management. And we have more exciting developments on the way. For instance, another big challenge has been the development of a system capable of autonomously navigating through granular environments, where approaches used by other robots, like for instance what you see being used by autonomous cars or tractors, don't work. And so we've been developing from scratch the world's first system able to autonomously map, localize, path plan, and operate in granular environments. And while more work is required to handle some edge cases, we're now at a stage where we can map and navigate through most new environments with high accuracy. We plan to release the first autonomous features commercially in beta in the next months. And we've gone beyond simple automation. What you see on the screen is the system autonomously and with no user input, determining which parts of what it sees is grain, shown in green, and which parts are structural elements like floors and walls, shown in red. This is at the core of enabling more advanced features, like for instance, the ability to measure with high accuracy the amount of grain in stock. A big part of choosing to apply the Crover effect to grain storage first has been the social and environmental impact of reducing post-harvest losses during grain storage and transportation, and making sure that more grain reaches the end of the supply chain uncontaminated. The environmental impact of using the Crover system has been validated by the Impact Forecast team. We're the leading provider of life cycle analysis in Europe. We estimated that a Crover system can save on average 670 tons of CO2 equivalent per site per year. Beyond grain storage, bulk solids and powders represent the largest family of traded commodities worldwide. And the Crover robots can work in most of those, from fertilizers and pellets used in the agricultural industry to other minerals and powders used in the manufacturing, minerals, chemical, and energy industries. The capabilities of the Crover robots also go beyond what any space rover is able to do, as current rovers aren't able to safely navigate through granular environments. Not only they cannot move below the surface, but they also struggle to move on granular slopes of less than 15 degrees inclination. And so the Crover technology is at the core of enabling the space ground missions of the future. And so while sandworms would not be able to move through the dunes of Arrakis, and BB-8 from the Star Wars movies does not work in sand, since the discovery of the Crover effect, movement through granular media is no longer science fiction. The future where we can reach below the surface has started, and it is now up to us to bridge the gap between fiction and reality. We just need to dig deep. Thank you.